Hello friends. So in the previous video we discussed about the quicksort, and today we discuss about the performance of the quicksort. So the quicksort performance depend on the partitioning, means how do you choose the pivot element. So if you choose a pivot element in such a way that your partitioning is balanced, then your complexity of your algorithm will be n log n. And if your partitioning is unbalanced, then your worst case complexity will be theta of n square. So this is similar to insertion sort, and this is similar to n log n. So it means in worst case your complexity will be theta of n log n, similar to the merge sort if your partitioning is balanced. So what is the unbalanced partitioning? So let's say your array is already sorted 1, 2, 3, 4, 5 and 6, and you choose this as a pivot element. Then every time your array will be divided, your problem into divided in two parts. One part will have n minus 1 elements and one part will have a single element. So the recursion function will look like the complexity of your n elements will depend on the sorting of the complexity of n minus 1 element plus complexity of sorting one element plus number of partitions. So in this case n partition will be there, because every time you are extracting one element from your original problem, so the complexity for partition will be theta of n. So if we solve this with the help of substitution method or master theorem, I will have a separate video for calculate the complexity in future videos with the help of master substitution. So, and this complexity will be theta of n square. So if I solve this with the help of mathematics also, so you remember that the if you know the basic of algebra, the 1 plus n. So let me do in a reverse way. N plus n minus 1 plus n minus 2 till 1 equal to n plus 1 by 2, and this will be the theta of n square, because this term gives the nth power as 2. So the complexity of the unbalanced partitioning will be theta of n square. Now let's talk about the best case in which you will get the balanced partitioning. So this is an example 5, 3, 6 to 10, 11, 12. So if I want to sort these numbers, so and if I choose 6 as a pivoting element, so if I apply the partitioning logic here, so what happens? All the elements which are lower than the 6 will be for the 6, and all the elements which are greater than 6 will come out after the 6. So this is the balanced partitioning, and this is also the best case. So if I write the recurrence relation for this, so the complexity of solving the complete problem will be the twice of complexity of solving the half problems plus theta of n, the complexity of partitioning. So at most n partition will be there, so it means the complexity will be less than or equal to the 2tn by 2 plus theta of n. So if you remember similar expression, we got the similar expression in case of merge sort, and the complexity was theta of n log n. So this is the best case complexity of quicksort, in which you get the complexity is theta of n log n, which is similar to the complexity of merge sort, but the difference is why people choose the quicksort as compared to merge sort, because the constant term in quicksort is much less than the constant term of the merge sort, and the merge sort has an extra thing which is called the merging of smaller sorted arrays. So merging of smaller sorted arrays does not exist in case of quicksort. Now this is another example of balance partitioning. So what is the balance partitioning means? In the previous slides we got that every time we are dividing the problem into two sub-problems. But in this partitioning, let's say you have an input size of n, and every time when you got the pivot element, you are dividing your problem into two sub-problems. One sub-problem as 1 by 10, another sub-problem as n by 10. So let's say you have 10 elements. So in one problem you are getting 1, and in another problem you are getting 9 elements. So this is the now at every step you are dividing your problem into two sub-problems. So if I calculate the complexity for this algorithm, so this tree will goes down till we get the size as a 1, and the height of the tree will be log n, and at every step the complexity of dividing the problem into sub problems will be the Cn. So the overall complexity will be height into Cn. So it means C n log n will be the complexity